So far in our journey through deep learning, we started with multi-layer perceptrons that took our MNIST images, flattened them into a long vector of 784, fed them into the input layer, and our model learned to classify them into one of the 10 digits. It was always 784 neurons in and always 10 classes out. A fixed, rigid contract. Then we moved on to convolutional neural networks, the superstars of image recognition. We trained them on data sets like ImageNet, where every input image was resized to a specific shape like 224 by 224 pixels to be classified into one of the 1000 categories. Once again, the input and output sizes were always fixed. So there's a fundamental constraint we've been working with up until now. These models demand that our world fits into a neat, fixed size box. An MLP needs exactly 784 features. A CNN needs exactly 224 by 224 pixels. So what happens when our data doesn't cooperate? What if I want to process a 5-word sentence or analyze a 100-word paragraph? Or what about classifying a 2-hour movie or a 15-minute short film? As standard CNN or MLP architectures simply cannot handle that. So the reality is most of the world's interesting data doesn't come in fixed sizes. Text can be a 2-word phrase like hello there or an entire novel. This is the challenge ahead of us. We need to build a bridge from the fixed size world we know to the variable size world of real data. That brings us to our goal for today. We will learn a powerful framework that can handle inputs of any size. But for now, we'll sidestep that a little bit with a clever trick. We will learn to compress them into a meaningful fixed size representation that allow us to return to the charted territory of fixed input models. So before jumping into complex tasks like machine translation, where we are dealing with different languages, variable length sequences, and all sorts of complications, let's start with the simple autoencoders. Autoencoders introduce an architecture that we need without any really complexity of having different types of inputs and outputs. The contract here, the autoencoder contract, is very simple. An input X, let's say of dimension D for now, like I said, we can have different size. So one easy trick can be if X can take different size, we just assume the largest possible size that X can take. And then we pad the rest of those empty dimensions. Okay, so with that, we have an input X, and we encode this using an encoder, let's call it encoder, to another space, latent space. The dimension of this latent space is much lower, and you can think of it like it is basically the concept that X carries with itself. And usually this has a much lower dimension that X. Of course, X has many paddings, and like, for example, in text, we have punctuation marks and etc. But the real meaning that this piece of text is carrying has a much lower dimension. So that's why usually the encoder really compresses the data. So to compute the loss, often we have to either go to a label space or a space that is similar to the space of X. So in the simplest case, let's just assume that we want to compress the data and we want to reconstruct it, right? So we want to reconstruct X with the same dimension. So we want the decoder to send back the latent space Z to the original space X hat. So in this case, what we are doing is basically we compress X to a latent space, and then we want this compression to be in a way that we can retrieve X to the best of our ability. So how we can do it? We basically want the reconstructed X to be very close to the original X. So some form of distance between these two that we want to minimize. And this will be our loss of this autoencoder. So this is much simpler than translation, where we have input X, for example, in English and the output in French, which is, let's say, a different space. Or, for example, the input can be images and the output can be captions, right? Again, different spaces. So for now, let's just focus on this simpler architecture, a very simple goal. We want to compress X in a way that we can retrieve most of the information in X later on. Believe it or not, you've been using this all along, but of course with a different disguise. Recall PCA, principal component analysis. In PCA, we had let's say, a d-dimensional input. After centering, so basically mean should be 0. We have some normalization here. So after doing that, we encode, or in other words, in PCA, we project the data into the top k principal components. So mathematically, this was where V was the matrix of principal component vectors, right? And Z was the compressed code that was in k dimension because of the k principal components. So basically, if you remember when we visualized that, it was like a rotation that finds the most variation in X. So for example, if your X was like this and you had two-dimensional data, it was enough to find this PC, which is now one dimension. Okay, so how we can decode this? We basically send this back to the original coordinate, which can be done by the same rotation, but the inverse, right? And here, since it's a rotation matrix, inverse is just a transpose. So PCA is simply finding the best possible linear encoder and decoder to minimize the reconstruction error. PCA works because compression works. The idea of compressing data through this smaller representation leads to a core concept in deep learning, the information bottleneck. So in the case of MNIST, for example, we had this 784 dimension, and we encode this to, for example, let's say a 32-dimensional latent space, which is much smaller. And then we could reconstruct the data with maybe some blur, but to most of extent, it's the same image. And this shows this information bottleneck that we are talking about. In other words, we don't want the model to memorize everything, right? We want the model to learn the patterns. And there are not really a lot of pattern here, as many as the pixels. So we don't need to really memorize the pixel. Instead, we learn the patterns, which are much lower dimension than that original pixels. This way, we enforce the model to learn an abstraction, remove noises, and find structures. So I encourage you to review PCA and how there we find these vectors, and through minimizing the MSE loss. Basically, we want to minimize an MSE loss like this. Note that there is no bias term here in this linear translations or rotation, just like a linear feed-forward neural network without activation. So you could, just similar to what we did in linear regression, of course, no bias. We have one linear layer and another linear layer. So what if we insert, just like what we did for MLP, we can insert nonlinearity in this feed-forward neural network, right? So like I said, in PCA, we have one linear neural network and another one here, again, linear. What if we add nonlinearity, just like before, and add more layers? So in this case, the model is no longer restricted to learning flat spaces. We've learned this before. It can now learn to represent data lying on complex curved manifolds, not just linear spaces, but very complex geometries. PCA cannot do that, but we can do it. We know how to do it. We call this an autoencoder, basically a PCA on a steroid, right? So now we have multiple layers with nonlinearity, and we do the same thing still. We do reconstruction. Still, we want x and x hat to be close to each other. But this way, we basically find a representation of x that is much richer and possibly even in much less dimension, because now we have richer representation. So maybe instead of 32, we could do much less for MNIST, let's say 10, for example. Okay, so this is basically a standard autoencoder that does the reconstruction. But we could do more, right? We could basically have an X and inject noise, so a noisy X, and we do the same architecture, but we demand a clean X. Okay, so this way we learn to clean the data. Or maybe we could do a supervised learning. So far, everything here could be unsupervised because we don't need to really provide any label. We have X and we just reproduce X, right? If we have a label, let's say X comes in, we find this nice latent features, and we want to decode this to some label. So in translation, the input can be English language sentence, and the output can be, for example, French, which can have different lengths. And Z here will represent the meaning of that sentence. We will code each one of these architectures.